So to begin my talk, in the Philippines, we deal with traffic in a very different way as you would have here in Europe. Europe and America, traffic here is very different than in the Philippines or in Asia. It's much more chaotic there. And this is an intersection in the Philippines where during really, really busy rush hours, you would have a lot of bottlenecks, and then you would have tiny enforcers trying to manage this thing. And it becomes a difficult thing to control, no? And you would think, maybe it's just really a matter of having signal control, proper signalized control, which is already something that our previous speakers have touched upon. And there was a time in 2014 when they installed new traffic light controls at a busy avenue in the Philippines. And the weird thing that they did is they decided, okay, it doesn't really work in the mornings. So what we're going to do is we're going to turn it off in the mornings. Let's have our traffic enforcers direct traffic, because there's just no way that our controllers are able to cope with this demand. And I mean, it sucks, but we try to make do with it. It works, but then you have fun things emerge, like you have this dancing traffic Santa enforcer that manages the traffic lights. So it's just a little bit of a funny side anecdote. It still happens until today, unfortunately. I checked. So one way is to, okay, let's have nice traffic signal control. And there are analytical approaches, such as the ones that Stefan Lammer was just showing us a while ago. But another approach that has come into prominence with the whole boom of reinforcement learning is trying to control traffic lights using this process. And this process of reinforcement learning is really all about trying to maximize this reward function over an extended period of time. And one way that you could try to maximize such a reward function, a simple way, would be to define what is called this Q value. And this Q value is really just an expected cumulative sum of these rewards. And then you could have a policy, which is, let us take the action that would maximize your Q value. And if you do this enough, you train a model to do this, eventually you will have a traffic controller, a reinforcement learning agent that can manage traffic. So sounds good. But the thing is, it's much more complicated than that. With reinforcement learning, it is very important to be able to define your rewards right. And if you define it incorrectly, something like this could happen. So this is a bottleneck simulation where the reward was to maximize the number of exiting vehicles. And then you have red vehicles that are agents that were trained to somehow intervene in traffic. And instead of actually what you would think that they would flow nicely, they are able to achieve a large reward score, but they're doing it in a very different way, something that probably would not align with how a traffic engineer would want to do this. So this is a problem if you have a bad reward function. So the best performing solutions here might not be your ideal or something that aligns with how we humans would expect a solution to behave. So that's why we came up with the idea. Now, yes, traditional approaches, model-based approaches are nice, but then in the cases where people really want to push for much more data-based approaches, we were trying to think, is there a different way to make this work for such systems? And what we came up with is, okay, what if we have at least two models that are optimized for different objectives? Is there a way that we could somehow combine these two models, let them run on a system, but how these models would operate on the system would be completely decided by the users of the system. So here we have vehicles. So the drivers in the vehicles would probably have some device where they could store their preferences. And then it's not that they're going to stop at the intersection and try to vote every time. No, they let a device do that for them. And then we have this hypothetical system where you can aggregate the votes and then use those aggregated votes to combine your queue functions from your deep neural networks. And we do that in this way where we are basically using the queue values for each action from both networks. And then we basically use the weights of your votes to combine them together. So in one queue network, your queue values would be different for each action. And it's basically telling you which actions are probably the best action to take at any point in time. And now you're combining two sets of actions based on some weights. And so we tried to devise a simple experiment to see if this would work. We chose two simple, very simple reward functions. Other researchers can define much more complex reward functions, but we wanted to see how far this would take us. And we needed to develop some sort of a baseline, so we would evaluate this scheme. So we have three different scenarios here. So we used a simulation based off of the traffic of Hangzhou in China. And if you look at the top row of roads, this is what the dynamics for the three different types of control would be. We have a queue network optimized for the stops, a queue network optimized for weights, and one that is using fixed time signal control. The weight network seems to perform the best. You have the most green. Green would mean moving vehicles at the maximum speed, and not a lot of stop vehicles. Stop vehicles you could easily identify from the red markers. So, okay, now we know what the baseline looks like. What were we trying to do with this voting thing? So imagine that you have individuals with preferences. This is something that Josh has talked about earlier. And these individuals can express their preferences, and those preferences can be used as inputs to your voting methods. So you could have binary voting where you just really take the maximum preference, and then that would be your equivalent vote. Or you could have cumulative voting where the preferences are preserved. We have other approaches for aggregating the votes. So we played around with these. We focused on the binary majority, binary proportional, and cumulative proportional schemes. And then we crafted three voting scenarios. So the voting scenarios are just different distributions of drivers with different distributions of preferences. So we have the bipolar preference distribution. We have a committed minority and indifferent majority, where the minority have very, very strong preferences, while the majority don't really care that much, and a completely random distribution of points. And this is what we get as the dynamics for the bipolar scenario, where you have the three different aggregation input and aggregation combinations. So we see that a lot of the red bands, the stop vehicles, are eliminated by combining different types of schemes. Although for the binary case, you still have a strong leftover effects of what the pure stops controller was doing. If you do it for the committed minority case, in general, you see that the proportional methods are mostly green, at least for this corridor. The same goes with the random distribution scenario. So in these different scenarios, we can see at least for the top row of roads, we have good performance. And now we wanted to evaluate this for the entire network as a whole. So what we did is we tried to plot the different values of the objectives for each of the different scenarios. And we try to represent them in terms of these triangles. Represented this way, it could give us the intuition that if you have a larger triangle, your multi-objective performance is better. It's a very simple way of looking at things, but it helps us analyze the different performances across the different scenarios. So if we do that plot for the different voting and aggregation methods, we can see that overall, you have large triangles, larger triangles than the baselines. And even compared to the baselines, these triangles are performing better, more optimally at some metrics. So we look at that for two scenarios. We have two scenarios, one where we were using the regular demand of that scenario, and then another one where we doubled the demand, so trying to simulate higher levels of congestion. And what we see here is you have the reference lines. So these lines are the baselines that we have. And then you can see that the box plots show the distribution of performances of individual vehicles. And what we see here is that most of them are already above the baselines, with the exception of binary majority schemes. I also added this other baseline, demand. When we originally published this work, we didn't compare it against the demand here. And what you see here is, but for the proportional voting methods, your performance, multi-objective performance, is greater than all of the other baselines that we could compare against. So this is interesting to us because nothing that if you look at the individual performances across the metrics, we would have expected that you would have a reduction in performance. In some cases, we have even an improvement. And because we're now looking at multiple objectives at the same time rather than single objectives, we're actually able to satisfy the performance criteria for the vehicles in the system. And another thing that we were looking at is this notion of satisfaction. So we simplified this way. We defined satisfaction as if you knew what the supposed action of your preferred intersection controller would be, at the next time step, would that be, or at the next switching of phases, would that be the action taken by the voting controller? And for the most part, if you have your binary majority cases, you can see that there is a separation of the satisfaction of your drivers. You can have a group that is highly satisfied, but then you will have groups that are very dissatisfied in this scheme. Whereas if you use proportional methods, you reduce this discrepancy between these two groups. So we found the scheme, and it works for this traffic system where you are not really sacrificing satisfaction for multi-objective performance. And at the same time, that multi-objective performance, or even for single objectives, is as close, as good as, if not better than, those of the pure controllers. So some takeaways from this work. We were able to enable self-organization in the system because what happens here is at every intersection, these controllers could be, or rather, drivers at every intersection could choose which controller would control that intersection at any given time. And because drivers would have their own priorities, these controllers would be responsive to the priorities of these traffic participants. And of course, for this system at least, we were able to show good multi-objective performance. It would be nice to see other systems where we could try to apply this and see how good it would still work. But some of the difficulties for that would be trying to find systems where it would be easy to apply the all of the inputs and things that you have to sense from the environment in order to run a proper simulation and do experiments. So I am ending a bit early for my talk, but I hope that you have some questions and we could spend this time having a good, productive discussion. Thank you very much.